Okay, right now what we're talking about here is our Unit 4 test review free response portion. These will deal with questions from chapters 14 through 17. One of the most difficult things that you're going to have with this is knowing which rule to apply and when, and to not overthink each situation. For example, on number 1A, we are told that if we have 38 passenger seats, what's the probability that all passengers who show up will get a seat? Well, if you're going to be looking at the information here, fight the urge to go too far and to think binomial, geometric. We have a probability model, and we know that 38 passengers, or all the passengers who show, will get a flight if we have 38 or fewer passengers. And looking at my probability model, that would happen if I have 36, 37, or 38 passengers. So that means I'm going to take the probability of 36, add to it the probability of 37, and add to it the probability of 38, for a cumulative probability in this case of 0.92. We don't need to do anything further than that because everything is distributed and shown on my probability model. Now, for part B is asking for the expected number of no-shows. And again, if we come back up to the table, if we have 41 people on the flight, that means there are no no-shows. 41, 1, and just keep going down the line. And that's how many no-shows there are. So you can use either probability model. You can use the probability model given to you, or you can convert it into a no-show probability model. Either way, when you're finding the expected value of no-shows, you can either think of that as 1 minus, or 41, sorry, minus the expected value of those who show using the original probability model, or convert it to the new probability model, and you should come up with the expected number of no-shows to be 4.1. Because from the expected model, from the probability model they give you, that number would have been 36.9. So you can work it either way. Problem 1C says, given that not all passenger seats are filled on a flight, what's the probability that only 36 passengers showed? For a problem like this, whenever you have the given, it's the probability of both. So the probability of 36 passengers and the probability that they are not all filled, which is the probability of both, over the probability of the given. Now let's take a look at that given for a second. If we're going to look at that given, what it is dealing with here is it's saying not all filled. If we look at the table, the seats are not all filled if I have 36 or 37 passengers. 38 is filled, and these guys we can disregard because that is an overfull plane. So, to do this, we can think about it as the probability of both 36 and not all filled, which is basically the probability of 36, so that's 0.46, over the probability that not everybody showed, so those are those two probabilities added up. So that's going to convert to 0.6053. Okay. As we move along, number 2, we have a categorical table here where we're fitting into multiple categories. And number 2A is asking for what's the probability that a person chosen at random will be in the 31 to 45 age group. Well, the 31 to 45 age group is this guy right here. We want to know the probability that they're going to be in that age group. So to find this one, we're going to take the total number of people who are between 31 to 45, and we're going to put that over everybody. So that is that number 89 over the total number, which is 207, which gives me a probability of 0.4300, because that's what it rounds to. For part B, what's the probability a person chosen at random whose incomes are over $50,000 will be in the 31 to 45 age group? Okay, this is another given problem. This is find the probability that somebody is going to be between 31 and 45 given that they are already making more than $50,000. So the probability for this is going to be the probability of both 31 to 45 and making more than $50,000 over the probability that they are making more than $50,000. So if we look at the table, and I want to talk about the probability that they are between 31 and 45, that's that column, and the probability that they are over $50,000, that's that column. What we're looking at is $35, 35 people, the one that classifies as both, over the total for the given, so over 96, and the equals 0.3646. Based on our calculations, it says, is income independent of age? You need to remember what the definition of independence means. Definition of independence says independent if probability of A is equal to the probability of A given B. And if we look at the first problem, the probability that we are in the 31 to 45 age group versus the probability that we are in that age group, given we make more than $50,000, we're looking at 0.43 compared to 0.3646. Those two are not equal, so it is not independent. Okay, again, two elements are independent of each other if the probability 1 is the same thing as the probability given a certain circumstance is met. Okay, number 3. You're talking about what would your recommendation be? Who is more expensive? Well, if we're going to talk about, let's go with machine A. The cost for machine A is going to be $1,000. Now, this doesn't matter how many repairs that you need, because you're automatically paying $50 a month, and there are 12 months in a year, and we're going to be going for 3 years. So no matter what, the cost of machine A is going to be $11,800. No exceptions. Absolutely none. We know that it's not even like saying an expected cost. It is the cost. There is no change in that. Whereas machine B is a little different. Machine B costs $10,500, and it's going to cost me $200 per repair. Well, the price then depends upon how many repairs we expect to get. So the expected value of repairs we have to calculate using our probability model, and the expected number of repairs is going to be 0.85. And so when I put that 0.85 into my formula, So that's going to be 0.85. My formula for the expected value of the cost of B, remember for expected value, multipliers, this being the multiplier and this being a constant addition, does affect both. So for the expected value of machine B, I can just plug that in, and I come up with 10,785 cents. So, who do we expect to be more expensive, or who do we expect to make a better purchase? My recommendation would be machine B. Simply because the expected value of cost is lower than machine B, for machine A. Now you could go through and you can calculate standard deviations and go through all that stuff, but the standard deviation is going to be significantly smaller, and it's not actually going to get me up to this. I went ahead and calculated it, and it is so, the expected value standard deviation of cost of B actually ends up to be $202. And just to get up to that 11,800, you are so many standard deviations away, you are almost guaranteed to have a better choice with machine B. It is an almost 100% better option. My calculator actually gave me back a 1 for the probability that machine B is going to make a better cost. Alright, here we go, your favorite stuff. Your rules of expected values and standard deviations with combining events. On number 1, we just want to know, is it likely that runner 3 will run a mile in less than 4.2 minutes? Well, if we're looking at runner B, or runner 3, runner 3 has an expected outcome of 4.5. His mean is 4.5. His standard deviation is 0.14. So to get to 4.2, it's going to be closer to down here. And if he is going to run less than that, if he's going to be faster, he's going to be on that side of the 4.2. So for this problem, we know that the mean is 4.2, standard deviation is 0.14. The answer to the problem is what I'm going to get from doing the normal CDF of, you could either do 0 or negative 99, whatever you'd like, but faster is faster, up to 4.2. I'm sorry, the mean was 4.5. Let me correct that real quick. With a mean of 4.5 and a standard deviation of 0.14. And when you calculate that, you get approximately 0.0161. And it says, is this likely to happen? Well, that's just shy of a 2% chance of it occurring. So I would say that this is probably not likely. Okay? And again, you can't just answer yes or no to a problem like this. You have to back it up. And the work is really worth more than just the yes or no. For part B, it says the distribution of team is approximately normal. What are the mean and standard deviation? The mean of all of the runners added up together is just the sum of all of their means. So it's 4.9 plus 4.7 plus 4.5 plus 4.8. So the expected value of all of their times is 18.9. Standard deviation is a little bit trickier. Standard deviation of all of the events added up since you're adding events, you have to still understand it's going to be the square root of all of their standard deviations squared. So 0.15 squared, 0.16 squared, 0.14 squared, and 0.15 squared. And when you calculate that, you get 0.3003. Now, for the last problem, on number 4, to suppose the team's best time to date is 18.4 minutes. What's the probability you'll beat the time? Well, you beat the time if the value is less than or equal to 18.4. So looking at a normal model where the mean is again that 18.9, the standard deviation is 0.3003, you beat the time if you are faster than 18.4. So for this problem, again, we go back to the normal CDF. And we're going to run less time than 18.4, so from 0 to 18.4, with the mean being 18.9 and the standard deviation being 3.003. Now again, hard to beat the best, so the amount of time it takes is 0.0480. Okay. Now, you gotta love problem number 5. Number 5 is we're switching into the gears of geometric versus binomial distribution. Remember, geometric is when you're looking for a first or until, and binomial is counting the number of successes within a set number of trials. So number 5A, we have 50 widgets. How many would you expect to be defective? We have a set number. We're looking for an expected value of that set number. So this is a binomial distribution with 50 outcomes and a chance of success of being 0.08. So the expected value of that is n times p, which is 50 times 0.08. So the expected value is 4. The standard deviation of this is the square root of NPQ. So it's the square root of 50 times 0.08 times 0.92, which gives me a standard deviation of 1.918. For part B, what is the probability that exactly 5 will be defective? Again, we're talking about that same binomial model. Exactly means I can do a PDF for a specific or particular value of out of 50 with the probability of it being defective to be 0.08, of having 5 of those. It's going to be about 0.1623. The probability that more than 4 will be defective, well, more than 4 means that I'm looking at these guys here. It's not 4 or more, but more than 4, so I'm eliminating those. And since I'm eliminating the numbers on the smaller end, I'm going to say 1 minus the binomial CDF, because it's a range, of out of 50, probability of 0.08, going up to 4, because we're subtracting this. And when you do that, you get 0.2037. Remember, at any time of this, if you want to check, I'd really highly recommend that you check and make sure that you can enter these into your calculator properly, because that really is part of the work here. Now, D kind of switches our language a little bit, and we're saying what's the probability that no more than 5 will be defective? Well, that means that of the 50, no more than 5 will be defective, means it's okay for 5 to be defective. We're not wanting the rest of them. So I've got this lower run, so I can just do straight up the binomial CDF of out of 50, 0.08 probability. We want to have up to 5. And that gives me 0.7919. And just a little FYI, to show your work for something like this on the AP test, you would need to state your binomial condition. You would need to state, where did it go? This guy up here. And then you would need to somehow express this portion down here. And the way I would probably do that is I would say the probability of 0 or of x equals 0. Let me change it to something that's a little bit more legible. Plus all the way up to the probability that x equals 5. Now the next one is talking about what's the probability that exactly 4 are defective. That's the probability that x equals 4. Again, showing your work would be listing that binomial model. The probability of x equals 4, and in our calculator, that's a binomial PDF, because it's one particular value, of out of 50, chance of success of 0.08 of having exactly 4. And that one gives me 0.2037. F changes directions yet again. First, whenever we talk about going until an event occurs or looking for the first of a certain kind of event, we are switching gears. And now we're talking about a geometric probability where the chance for success is 0.08. So for this one, we're going to do geometric probability of 0.08 that it happens on the 5th trial, which is the same thing as saying we have 4 failures, and probability of a failure is 0.92, and 1 success. And when you calculate that, you get 0.0573. Part G says how many widgets would you expect to pick before finding a defective one. So this is saying, again, before is the same thing as an until problem. So still with your geometric distribution, the expected value for something like this is 1 over the probability. So 1 over 0.08 is going to be 12.5. And for the last one, what's the probability that you pick a defective widget among the first 3? That means it's either the first one, the second one, or the third one. So we're still using the geometric model from up here. And we're saying what's the probability that it happens on the first, plus the probability that it happens on the second, plus the probability that it happens on the third, which is calculated by doing either each of those separately PDFs or doing a CDF of 0.08 up to the third event, which gives me 0.2213. Flashback. Going back in time. Talking about chocolate ice cream, vanilla ice cream, and both. And that word both in a situation like this, 9 times out of 10, I'm going to draw a picture. So, I have chocolate, I have vanilla, and I have a very difficult to read circle. So let's try that again. Let's make it big enough so that I can actually put numbers into this figure. I'm not a perfectionist at all. So we have chocolate, we have vanilla, and we have both. So, whenever you deal with this, you always put the both in the middle and subtract, working your way out. 68% like chocolate, so 68 minus 36 is 32. 42% like vanilla, so 42 minus 0.36 is 0.06. And then the whole thing is worth 1, so subtract all of those and you get the probability of none of them to be 0.26. So when they talk about what's the probability that somebody likes only vanilla is just that section. So only vanilla is going to be 0.36. I'm sorry, 0.06. Of the students that like vanilla, so for this one we're given vanilla, what is the probability that they like chocolate? So the probability that they like chocolate, given that they like vanilla, is the probability of both, chocolate and vanilla, over the probability of the given. So the percent that are in the chocolate and the vanilla, that's 0.36. The percent that are in total in the vanilla, either looking at the Venn diagram being both of those two, or the given statement, 42% like vanilla. So the probability that somebody likes chocolate given that they like vanilla is actually 0.5294. Are the events like chocolate and like vanilla independent? Well, again, independent means if the probability of chocolate is equal to the probability of chocolate given vanilla, well, we've already seen up here the probability of chocolate is 0.68, and the probability of chocolate given vanilla is 0.5294. Those are not the same, so they are not independent. And they've got to be the same right now. Are the events disjoint? Disjoint happens if the probability of two events in their overlap is equal to 0. Well, the probability of chocolate and vanilla is equal to 0.36. That's obviously not 0, so these guys are not disjoint. There is an overlap, they are not disjoint. Winding down our problems now. Okay, we want to figure out what is the probability that my bowls are going to overflow. In order to do that, you have to define what it means for a bowl to overflow. It will overflow if I pour more than there is room for in the bowl. So if I were to do that as an equation, the pour minus the bowl has to be greater than 0. That's when something overflows. So we're going to need to find the expected value of the pour minus the bowl and the standard deviation of the pour minus the bowl. Well, the expected value for this problem here is going to be the expected value of a pour, which is going to be 2.5, minus the expected value of the bowl, which is 2.3, which is 0.2. I'm sorry, it overflows, yes. Pour is greater than the bowl. And so I've got these two backwards. Sorry, I knew there was something wrong. So 0.3 and 0.5, so it gives me a negative value. Standard deviation, remember, it doesn't matter if they're talking about add or subtract. You always add with variances. And you always, once we're in here, we have to do the squares. So the variances here are 0.4 squared and 0.3 squared. And so that gives me an expected standard deviation of 0.5. So again, it's going to overflow if P minus B is greater than 0. So if I look at my normal curve, and I have the expected value here is negative 0.2. Standard deviation is 0.5, and it will overflow if I'm greater than 0. 0 is going to be up here. So I'm going to do normal CDF from 0 to a bunch, standard deviation, expected value, standard deviation, and my final probability ends up being 0.4330. So we expect overflow to happen 0.4330% of the time. or if you have a toddler pouring the bowl. Hee hee hee. Number 8, 23% of adults smoke. Of those who smoke, 57 develop lung disease. Of those who don't smoke, 13% develop lung disease. Immediately I have conditional probability. I want to do a tree diagram. So I'm going to have smokers, and I'm going to have non-smokers. Smokers are 0.23%. Non-smokers would then be 0.77. And then we have lung disease. Well, we're going to have no lung disease. So I'm just going to put healthy. Lung disease or healthy. Lung disease or healthy. Of those who smoke, 57% develop lung disease. So that means that 43% do not. Of those who don't smoke, 13% develop lung disease. So that would mean that 0.87% do not. And if I go through and multiply these guys out to find the relative probabilities for each of them for the total population, I have 0.1311, I have 0.0989, I have 0.1001, and I have 0.6699. The problem says find the probability that someone with lung disease did not smoke. So here are my folks with lung disease. So what I'm going to say is we're going to find the probability that somebody with lung disease, that's what I'm given, did not smoke. So to do this one, I'm going to do the probability of both. Probability of non-smoker and lung disease over the probability of lung disease. So that's going to be non-smoker and lung disease over the probability of lung disease, lung disease, when you add those two together, you get 0.2312. And that gives me a probability of 0.4330. Nope, sorry, that was, yeah, 4330. I'm sorry, I wrote this answer down. That was the answer to the next problem, so actually, let me go ahead and calculate what the answer to that one is. Let's see if I can find my calculator. Okay, so that previous problem I accidentally wrote down the wrong answer to. That's going to be the normal CDF going from 0 to some big number. Mean is negative 0.2. Standard deviation was 0.5. And there we go. 3, 4, 4. What was the last digit? 6. There we go. Sorry about that. Okay. Keep on keeping on. Number 9, game of chance involves spinning a spinner. This is the amount that you would win. Create a probability distribution for this model. Okay, so my variable X is going to be the amount you win. You have to define your random variable. So that way, when I set up my probability model, it stands for something. I can start winning. The goal is at $100. And then we can get down to 25, down to 10, down to 5, and then nothing. Probability of getting the 100 was 0.02. Of 25 is 0.08. 10 is 0.20. 5 is 0.30. 0 is 0.40. And again, I would put this into my table, this being my list 1, this being my list 2, finding the expected value, using list 2 as the frequency. So the expected value of X means 7.5, the standard deviation of X is 14.87. Interpret these contexts That means you expect to win $7.50 with a standard deviation of $14.87. That's all you need to write there. You don't need to draw a normal model or anything like that. For number 10, again, we're going to do the expected value. So we know that if X is your ice cream, and the expected amount of ice cream for you to have is 6.4, and the standard deviation of your ice cream is 1.4, we can use that to find the expected value and standard deviation of the cost. Cost is going to be $1.50 plus 15 cents per ounce. So the expected value, it's easier to write it like this for this one, of 1.50 plus 0.15x is we get to actually just apply those rules straight to the expected value. And so that's 1.50 plus 0.15 times 6.4. The expected cost of a cone would be somewhere around $2.46. For the standard deviation, still doing it off of the same equation, but we've got to think about what actually affects the standard deviation. A constant addition does not affect the standard deviation. A multiplier does. Now the nice thing about this is even though I have a multiplier, I'm not combining multiple things. I'm not doing 0.15 events, I'm doing 0.15 times it. So all I need to do is do 0.15 times the standard deviation. You need to use the square root when you are combining events, and this is no combining events, so I don't need it. The standard deviation here is going to be 21 cents. Okay, almost done. Number 11. We have to first define our situation. Miss Vaughn's scores will top Miss Lake's. So that's Vaughn is greater than Lake. Also translates into Vaughn minus Lake is greater than 0. Because we need to have a number there in order to do our probability models. Now, the expected value of Vaughn minus Lake is simply their independent expected values, the difference between them, so it's negative 41. The standard deviation of Vaughn minus Lake is a little different. We are combining elements here, so I need to take the square of each of their standard deviations. So I'm going to get 21.5 for that. Now Vaughn is greater than Lake when we find their difference and it's greater than 0. So here's my mean. Standard deviation is 21.5, so that's just shy of 2 standard deviations away. So I'm going to put it right here for 0. And greater than is shading over here. So this is the normal CDF going from 0 to some big number with a mean of 41 and a standard deviation of 21.5. That happens 0.0283 for probability. Now, on the last piece, if we are combining their scores, the expected value of their combined score is combining their expected values. So it's negative 41. I'm sorry, that was the previous one. So it is 291. And the standard deviation of the sum is actually going to be the exact same thing as the standard deviation of their difference. So I'm just going to go ahead and write that down. And we want to know the probability that their combined score will be bigger than 320. So that means that if I have an expected value of 291, standard deviation of 21.5, it's going to be just over 1 standard deviation. Let me make that a little bit closer in. So that's my 320. So I'm going to do a normal CDF, going from 320 to really, really, really big, with the mean of 291 and a standard deviation of 21.5. And I come up with 0.0887. We are finished. Alright, I hope this helped you out a little bit. Like I said, the solutions to the multiple choice part will be posted separately for your viewing pleasure. Have a good day.